Hello, everyone. Today's topic for covalent bonding is polarity. Polarity has to do with the unequal sharing of electrons in a bond. So, when we went through the periodic table, we covered a bunch of trends, but polarity focuses on, or it's centered around, electronegativity. So, in covalent bonding, the electrons are supposed to be shared. But if you remember what electronegativity is the ability of an atom to attract electrons. And let me open up a periodic table for the purpose of the trends. So in the first slide, they give you the example of chlorine and hydrogen, okay, HCl. In this image, you can see that the right side is red and the left side is blue. The red side is the side that has most of the electrons. So this is showing that the electrons are a lot closer to the chlorine than they are to the hydrogen. And the reason for that is because chlorine has a higher electronegativity. Electronegativity increases, again, going up and to the right. Chlorine is here, hydrogen is all the way over here. So chlorine has a stronger electronegativity, so the electrons are going to be closer to the right than they are to the left. And what that does is it makes a temporary pole. Okay, what I mean by pole is two charges. So now the way they draw this is supposed to be an arrow, and we've gone through this a little bit in the past. Notice how they have you see a plus sign on the left side, and then there's nothing on the right. This is the positive side, and this is the negative side. This is the negative side because the electrons are over here, and if you remember, electrons are negative. So, and then this side is the more positive side. So it creates a temporary pole where the left side is positive and the right side is negative. Okay, that's what this is showing you here. If you have the same element, like in oxygen where it's O2, nitrogen where it's N2, chlorine where it's Cl2, things like that, if they're the same, that means they have the same electronegativity. And if they have the same electronegativity, that means the pull on the electrons are equal. And if they're equal, then it just stays center, and one side isn't more positive or negative than the other. So that's where nonpolar bonds come from. Now, the type of bond you get, there are some rules. Okay, so you just have to follow the numbers. So if the difference in electronegativity is less than 0.4, you have a non-polar bond. Okay, this would be a non-polar bond. You have the exact same atom. If you have the exact same atom, the difference between them is going to be 0. So there is no bond. If it's between 0.4 and 1.7, then you have a polar bond, and if it's above 1.7, you have an ionic bond, which is the topic we were covering before the school closure. And you only get these between metals and nonmetals. Ionic is the strongest type of bond in terms of the pull, and that's between metals and nonmetals. But for covalent, you either have nonpolar or polar. And here is a table where they give you the electronegativities, and now we have numbers to work with. So for the first one, it was chlorine and hydrogen. If you look at the table, chlorine would be a 3 on the electronegativity scale. Hydrogen is 2.1. 3 minus 2.1 is 0.9. 0.9 would fall between 0.4 and 1.7 and would make it a polar bond. Fluorine is 4, but 4 minus 4 is 0. So this would be a nonpolar covalent bond, which is what you have here. What is the electronegativity between hydrogen and nitrogen? So let's do some examples here. Nitrogen is 3, same as chlorine. 3 minus 2.1 is 0.9. So 56 would be A. Does nitrogen hydroxide contain polar bonds? This should be a yes or no question, not true or false. But it's asking, does it have polar bonds? The difference is 0.9. 0.9 would fall between 0.4 and 1.7, so it would be polar. So 57 should be true, but it should be a yes/no question. What is the electronegativity difference between boron and hydrogen? Boron is 2, hydrogen is 2.1. The difference between them is 0.1. So this would be C. And then the bonds, therefore, in BH3 would be considered what? 0.1 is less than 0.4. So the bond type would be considered non-polar. So 59 should be B, non-polar covalent. Yeah. Now we just went through the polarity of individual bonds. You can have bonds be polar, but the molecule in general can be nonpolar. So you can have polar bonds, but a nonpolar molecule. How is that possible? If the poles cancel each other, that's how that's possible. So in this case, we have CO2, and this is what CO2 would look like. We have carbon double bonded to both oxygens. This goes back to the molecular geometry, which was the Vesper stuff, which was yesterday. This atom or molecule would form a linear shape, meaning in a straight line. On the left side, you have an oxygen. On the right side, you have an oxygen. Oxygen is more electronegative than carbon. Let's go to the table and see what's the difference would be. So oxygen is 3.5, carbon is 2.5. The difference between them would be 1. 1 would fall in this category and you would have a polar bond. So the bonds are polar. Look at the arrows. So this arrow is saying that the electrons are being pulled towards the right, and this one is saying the electrons are being pulled toward the left. But because the pulls are equal, these are two oxygens, they have the same strength when it comes to the pull. They're being pulled in opposite directions. Think of carbon in the middle and you're playing tug of war. They're equal in strength. Because they're equal in strength, the pulls actually cancel. And because they cancel, you end up with a non-polar molecule. Okay? So just because there are polar bonds, does that mean the molecule itself will be polar? So this molecule is not polar because the poles cancel each other out. Okay? Now let's look at water. Okay? This is an example of water. In this case, water forms a bent shape. So it's no longer in a straight line. Now we have a bent shape. Let's look at the difference between oxygen and hydrogen. Oxygen would be 3.5. Hydrogen is 2.1. So the difference is 1.4. Okay. If the difference is 1.4, it would be polar covalent. So oxygen is pulling the electrons towards it. So this is why you end up with the arrows going up this way. But because it's at an angle, the pools don't cancel. When you add them up, what you end up getting is this. This is the result. This is the result of those two pulls. So this one's pulling this way and this one's pulling this way. And what that results in is a total polar or dipole moment, what they call, of going straight up. Okay, so this is what you get. So you feel a force going straight up. Okay, when you add these two up, you get the blue arrow. So what this is saying, by adding the individual pole or bond dipoles, what they're referring to is the red arrows, you can determine the overall. So this bottom arrow would be the overall. And this is telling you the conditions for polarity. In order for a molecule to be polar, it must contain one or more dipoles. This one has 2 of them. And these bonds must be arranged asymmetrically. Asymmetrically means, you can, because symmetrical means you have the same on both sides. Asymmetrical is the opposite of that. It can get a little more, it's not that simple because technically this is symmetrical. The left side would be the same as the right side, but you still have a polar molecule. So I'm not too happy with that. You can have symmetry and still have polarity if things are not aligned properly. So I'm not 100% happy with this definition. I would say if you have one or more dipoles and they don't cancel out, you have a polar molecule. Okay, so I would add another one C here. They can't cancel out, and they give you some more examples down here. So in this first one, we have HCl. HCl we already looked at. Let me zoom in a little bit because the arrows are not easy to see. HCl is being pulled towards the right. There is nothing to cancel it. There's nothing to cancel it, so this would be polar. This is a polar molecule. This one, you have one being pulled up, and you have three being pulled down at an angle. These would actually cancel, okay? If you think about it, you can make sense of it. This is being pulled straight up. These are all being pulled down at an angle. If you think about the X and Y, these would cancel each other out in terms of the X-axis, meaning there would be no left-right movement. And because they're going slightly down, they would cancel the Y portion as well. So there would be no net dipole. So this would be a non-polar molecule. This is non-polar. This is non-polar. Scrolling down a bit. Boron and fluorine. This is a trigonal planar molecule, or that's the shape. These would cancel, okay? They would cancel. This is a non-polar. The reason these would cancel, the angle between them are all the same. This is 120, this is 120, this is 120. The angles are all the same, and you have equal pull in every direction, okay? So this would result in cancellation. Only because the angles are all the same. If the angles were a little different, then those would not cancel, but because the angles are all the same, that is non-polar. This is polar. You can see there's no arrows between the carbon and the hydrogen, and the reason for that is if you go back to the table, carbon is 2.5, hydrogen is 2.1, so that is 0.4. 0.4, I know it says it has to be less than 0.4, but this has to be greater than. If it's exactly 0.4, it would still be considered nonpolar. So between carbon and hydrogen, it's nonpolar, so there's no pull. So chlorine wins, and the overall pull would be up. This would be a polar molecule. It does have a overall direction. And then these are all pushing slightly towards it. If you were to add up those arrows, the net one would be one arrow going straight up like earlier. This one would be polar. So we have two polar and three nonpolar in this example. Okay. And then the last slides go through a bit of polarity. It says the polarity of a molecule affects the melting and boiling points. Why? So if we think about, let's think about water. Okay, let's think about water. Let me zoom out a bit. Let's think about water. So let me draw water again. So this is why polarity is important, is because it affects how molecules interact with one another. So the oxygen is more electronegative than the hydrogen, right? So the electrons are being pulled towards the oxygen. So I'm going to say this is negative. And again, you have to think about these as temporary. They're not literally negative and positive, but that's like how the charges are distributed. So we're going to say the hydrogens are positive and the oxygen is negative. And let's draw another water molecule. And I'm going to draw it like this time. No, let me not draw it that way. Let me draw it the other way. And the same thing, the oxygen was negative and the hydrogens are positive. So if you had two water molecules, what's going to happen is you're going to have the oxygen be attracted to the hydrogen because opposites attract. This is negative, this is positive. It's going to want to get pulled. And the same thing here, okay? The water molecules are going to be very attracted to one another. If you ever played around with water, water can be sticky, if that makes sense. It's not sticky in the sense that you feel like sticky on your finger, but if you look at the way water interacts with itself, like if two drops were about to run into each other, like they just combine instantly. And the reason for that is because they're so attracted to each other. And they're so attracted to each other because of the polarity. So on this table, they give you different boiling points. So H2, you have the same element. If you have the same element, that means there's no difference in electronegativity. So H2 would be non-polar. Because it's non-polar, you have this very low boiling point. CH4 is also non-polar if you look at the differences in electronegativity, and that is also why it has a very low boiling point. It has a bigger boiling point than H2 only because it has a carbon in it and it has more molecules, so it's bigger. NH3 is polar, but barely. Because it's barely polar, it also has a very low boiling point. Now you get into SO2. SO2 is a lot more polar than these, which is why it has a higher boiling point than the rest of them, but it's still pretty low at -10. But if you look at water, water boils at 100 degrees Celsius. And the reason for that is because it is indeed polar, and the polar or the polarity of it causes the molecules to be attracted to one another, and that gives the high boiling point. This is why water boils at 100 degrees Celsius, because it's polar. That's where that comes from. And let's do some examples before I get into the worksheet. So this is saying which of these are polar molecules. This goes back to the shape. Water. Water we already know is polar. We did the example already. CO2. CO2 would form what shape? If you remember earlier, CO2 is linear. It'd be in a straight line. The poles would cancel. So B is nonpolar. CH4 is nonpolar. We already looked at the difference between them in electronegativity. Oxygen would be nonpolar, and it's nonpolar because you have the same element. Same element means equal pool. Equal pool means they cancel out, and you have a nonpolar. So this is nonpolar, this is nonpolar, and this is nonpolar. The water is polar, and now let's look at the carbon and oxygen. You have two atoms. If you only have two atoms, it's automatically in a straight line. Now we just have to look at the difference. Carbon is 2.5, oxygen is 3.5. The difference between them is 1. And so, if the difference between them is 1, you have a polar covalent bond. So it is indeed polar. So the answer to this one would be A and C. So this would be C. 61 is sulfur trioxide polar. This is the last one I'll do before we get into the worksheet. So to do this, we got to draw it. We have to draw it. We have SO3. How many molecules are we working with? Or not molecules, how many electrons are we working with? Sulfur and oxygen are in the same group, so they each give us 6. We have 1 sulfur and 3 oxygens, so that's 6 times 4. 6 times 4 would be 24. Okay, 6 times 4 would be 24. Put the dots on them. Are the oxygens happy? Yes, they are. They each have 8, 8, 8, and 8. How many electrons have we used up so far? 8, 16, 24. We've used up all 24. Is the sulfur happy? Sulfur is one of those that is perfectly fine with 3. Okay? Sulfur is one of those that is perfectly fine with having just 3 bonds, meaning 6 electrons, kind of like boron. Okay? Sulfur can sometimes also have more than 4 bonds. Okay? So sulfur is one of those exceptions that can be a little funky. But this is the shape, or this is what the Lewis structure looks like. Now, from the Lewis structure, now we have to follow the Vesper model. So if you remember from yesterday, what will be the Vesper number? You have 3 numbers. The first number is the bonds and the lone pairs on the middle one. How many bonds do we have? 1, 2, 3. How many lone pairs do we have? 0. So this would be 3. The second number is just the bonds, and we have 3 bonds. And the final number is lone pairs only, and there are no lone pairs, so this would be 3, 3, 0. So in 3, 3, 0, what shape do we have? Let's go back up from yesterday. Let's look at the table. 3, 3, 0 would give us what? 3, 3, 0 is going to give us trigonal planar. And trigonal planar looks like this, okay? So you have an atom in the middle, and all the angles again are going to be 120 degrees, and it's going to look like that. That is going to result in cancellation, okay? So if I were to draw this a bit clearer, well, I think it's fine the way it is, so I'll just stick with it. Let me switch to blue. The oxygens are more electronegative than sulfur. So this oxygen is pulling the electrons that way, this oxygen is pulling the electrons this way, and this oxygen is pulling the electrons that way. Because they're all the same atom, they're all oxygen, that means they have equal pulls. And because of the angles, how it's set up, these pulls are going to cancel out. So is sulfur trioxide polar? The answer is no. So this would be B, false. It is not polar. Okay, because the pulls cancel out. To answer these questions, you have to combine the stuff we did yesterday with the Vesper theory with the shape or with the electronegativity and polarity that you learned from this unit. You have to combine the two topics, okay? And I'll actually do 63 because 63 covers the boiling topic that you should understand a little bit. At least, like, it's important for you to know. Why does alcohol vaporize before water? Why does oil boil at like 400 degrees Fahrenheit? What affects these things? And polarity is what affects these things. And you can guess the boiling points of things based off of the polarity. So it says, which of the following would you expect to have the highest boiling point? So Cl2 would definitely be in last place. Why would it be in last place? It's because it is nonpolar. You have the same atom. You have two Cls. The poles would be equal. You would have no polarity. So this I would expect Cl to be the lowest. Okay, this would be the lowest boiling point. Okay. And then CCl4. So CCl4 would look like this. If we were to draw the Lewis structure or finish it. How many electrons are we working with? You have 7, 14, 21, 28 plus 4. We have 32 in our bank. And then if we do the dots, everyone will be happy. Okay. The chlorines are all happy. They each have their 8. The carbon's happy. It has its 8, 2, 4, 6, 8. And if you add up the electrons, you have 8, 16, 24, 32. We've used up all 32 and everyone's happy. This is what it would look like. The numbers for this would be 4, 4, 0. 440 would result in tetrahedral, if I'm not mistaken. Okay. 440 would result in tetrahedral. So 440. All the angles would be the same. If all the angles are the same and all of these atoms are the same, they should all be chlorines with carbon in the middle. What do you expect the poles to do? If you guess that they're going to cancel, you would be correct. Okay. So because of the shape, these poles, even though they are polar, they would cancel. The chlorines are each pulling equally, it would cancel out. So this is also non-polar. So Cl2 and CCl4 are both non-polar. This one would boil after Cl2 though, because it's a larger molecule. Okay, if you were to think about the interactions between them, it would be harder to pull them apart because they can get tangled up a bit more, if that makes sense. So this would be in second place. So this one has the lowest. This I would put in the middle. Okay, and HCl would be the highest because it is the only polar one. Now this is just what we expect, okay? Sometimes it isn't always the case. So based off the polarity that we just learned, we would expect HCl to have the highest boiling point, but sometimes there are other factors to take into consideration. But HCl we would expect in this case to have the highest boiling point. Okay, now let's switch over to the worksheet. How long has this thing been so far? Okay, 27 minutes. I try to avoid making them too long, but sometimes can't really help it. Which one has the most complications? More or less, the questions are all the same. Okay, so I can pick any. I can pick any two, and it will be okay. Let me do. I'll do number 1 in the classwork. I'll do number 1 and number 3, just because this has SF6, which can be a little complex. So I'll do number 1 and number 3. So let's draw it, because we have to draw it in order to answer the questions. So consider N2F4. So we've seen N2F4 before. It would look like this. This is what it would look like. So A ask, is the NF bond polar? So just the bond between nitrogen and fluorine. To answer that question, you just have to look at the table. Or not the periodic table with the electronegativity numbers. Nitrogen is 3. Fluorine is 4. 4 minus 3 is 1. If the difference falls between 0.4 and 1.7, it is polar. 1 would be between these two numbers, so it would be polar. So A would be yes, it is polar. Why? Because the difference falls between 0.4 and 1.7. Is the NN bond polar? So it is talking about the bond between these two nitrogens. The answer is no, it is not polar. Why? They're the same atom. Same atom means equal pull. Equal pull means they cancel out. And then C asks, is the whole molecule polar? Okay? Is the whole molecule polar? Now this can get a little complicated in this case because you have two central atoms. So two central atoms is going to give you a weird shape, but let's just focus on one. So let's say we're looking at this one nitrogen. So what are the Vesper numbers for it? We have, remember there are three numbers. The first number is the bonds and lone pairs. So this nitrogen has 1, 2, 3 bonds and one set of lone pairs. So this would be, let me change the color, this would be 4. How many bonds do we have? Just bonds. The second number is just bonds. We have 3. And we have one lone pair. The last number is just lone pairs. Again, these two numbers should add up to the first. So we have 4, 3, 1. What does 4, 3, 1 look like? Oh, I have to switch over to the other slides. My bad. 4, 3, 1 would be what? Oh, I went up a little too far. 4, 3, 1 would be trigonal pyramidal. Okay. 4, 3, 1 would be trigonal pyramidal. So you have this lone pair up top, and everything is being bent downward. So what you have in this case is, so this is nitrogen in the middle. So this is the nitrogen in the middle. You would have the lone pair up top. These two right here, this would be the fluorine. This would be the other fluorine. And this would be the nitrogen with the other two fluorines attached to it. So this is what it would look like. So now we can look at the pulls. Fluorine has a stronger pull. So this is going to be going from the nitrogen to the fluorine. So let me label this. So this is nitrogen. This is nitrogen in the middle. You have a pull going towards the fluorine here, and you have a pull going towards the fluorine here. There is no pull over here. There is no pull over here because they're equal. So you have a polar moment here. If we were to focus on this nitrogen, the same thing would happen. You would have, it would be pulling it downward, same as before. So you have a pull over here, and you have a pull over here. And they're both going slightly down, or they're all going slightly downward. So you would have a total polarity of something like this. Okay, it would, if you were to add them all up, you would have a total pull of something going down. If you add them up, it would be going downwards. So this would be considered polar. Is the molecule polar? Yes, yes it is. Okay, so this is yes, this is no, and this is yes. Okay, and the explanation is just the shape and the non-cancellation of the poles. So that would be N2F4. And if we do SF6, three, 4, 5, and 6. How many electrons are we working with? You get 7 from each fluorine. So 7, 14, 21. 28, 35, 42, and then you get 6 from the sulfur. 42 plus 6 equals, we have 48 electrons in our bank. And for the sake of time, if we put all the dots on the fluorines, you'd have 8, 16, 24, 32, 40, 48. Okay, so this is what it would look like. And then you just have to put the dots on all of them, all the fluorines. But for the sake of time, I'm not going to put the dots. But this is what it would look like. So if we do the Vesper numbers, again, 3 numbers. First number is just bonds on the central atom. You have 6. Well, the first number is bonds and lone pairs. I'm sorry. There are no lone pairs on the sulfur. You just have 6 bonds. So this would be 6. The second number is just bonds. So again, this would be 6. And then there are no lone pairs. So it's 0. So you have 6, 6, 0. So 6, 6, 0. Got to switch over again. I'm sorry. 6, 6, 0 would be this octahedral. So you have a sulfur in the middle. You have a sulfur in the middle, and the rest of them are fluorines. Okay. These are all Fs. Okay. This is what it would look like. I'm actually glad they have the images on the slides because that actually helps a lot with the explanation as to why things cancel. Okay. These 4 fluorines. Okay, the 4 I'm talking about is this one, this one, this one, and this one. Those 4 fluorines are on the same plane. By the same plane, I mean like if you think about it like height. They're all at the same height. Okay. See how they call this square planar? Because they're on the same plane. So all of these fluorines, fluorine is the more electronegative one. So just know that all the poles are going towards the fluorine. Okay. So the fluorine is doing the pulling. These are all at 90-degree angles. Okay, so that's 90, that's 90, that's 90. Because they're all at the same angle, these poles would cancel. So this fluorine right here would cancel this fluorine. This fluorine would cancel that fluorine. So these 4 fluorines already cancel each other out. And then this fluorine up top is going to cancel the fluorine at the bottom. So just know that overall, the molecule is not polar. The poles cancel out. So is the molecule polar? No. Okay, this is no. The poles cancel out. But is the SF bond polar? Just look at the table. For polarity, sulfur is what? Sulfur is 2.5, fluorine is 4. The difference is 1.5. 1.5 would make it polar. So in this case, we again have the example of we have a polar bond, but we have a non-polar molecule. Okay? So A would be yes, and B would be no. Okay? So for polarity, you have to know the shapes. And you have to use the shapes to look at if things are going to cancel or not. You have to combine the shape stuff from yesterday with the polarity stuff from today. And that is the only way you'll be able to answer the questions. Again, if you're confused, you can always ask me. You can help each other out. But that's it for today's discussion. I wish you the best. If you have any questions, again, you can always ask. Keep fighting through it. I know it can get confusing sometimes. It's unfortunate what we're dealing with, but we got to do what we can do.